Hey.
Yeah.
Hi, good morning, good afternoon, good evening, wherever you are. My name is Roy Chowdhury, and before I start, I would like to thank Petroleum Engineering Association for allowing me to present through their platform. And I really look forward to interacting with you all. My I have about 38 years of experience, and that's a global experience working in various different parts of the world. And now, for most of it, about 35 of years was with Baker Hughes, and now I run and operate uh, upstream technical training where I create the content. If required, I deliver the courses on the subjects of various areas of well construction. So for the today's presentation, which is going to be say around 60 minutes or so, you would notice all these different areas that I cover in my detailed courses. I will use bits and pieces from all of these, and some are shorter sections, some are longer sections, but at the end of this entire presentation, I would love to address any questions that you all may have. Also, I have tried to put some references against the pictures that I have used in these slides so that you can refer it back to the SP papers that I'm using this information from. Just to highlight, I have spent significant amount of time as a technical instructor and managing the technical training wing of Baker Hughes. So obviously, this is something that I have done in my past life, and I love to present this to you. So let's get started. For the today's presentation, I intend to cover drilling performance, benchmark, and qualifiers, well classification based on the challenges, just a single slide. Especially all these are pertaining to the high angle well. When we say high angle well, we are referring mostly to the horizontal or anything, let's say, above 70 or so. And I will give you a reason why this window becomes kind of important for us to understand. Drilling dynamics, I plan to cover. We'll have few kind of pointers for torque and drag. I will also try to cover a point or two about the drill bits, because that's also very important area when you are choosing a drill bit. And of course, at the end, we will cover hole cleaning and we will summarize the entire presentation. Now, drilling performance benchmark. This is probably a very important topic because, drilling for oil is a expensive and a complicated business. Now, you cannot improve if you can't measure the current performance. So for us to be able to improve upon the performance, we need to have a correct understanding of the performance. And when we talk about the performance, there are most common kind of formats or plots that we use. You see on the right hand top, that is the depth and the ROP. I'm sure everybody at one stage or other has seen this. And one on the bottom is hours per hole section. This is mostly a very high level picture that you see as a plot hanging on the companyman's desk. And he puts the day depth curve or hour against the depth curve just to monitor the progress. The top one is though very common, but it doesn't give you the entire information that you are looking for. For example, if you look at these 4 runs, it would not tell you that what kind of drilling systems or the drive system it has been used for the specific purposes. What was the bit that was used to drill these sections? what was the pressure, differential pressure at the bottom? When I say differential pressure, I mean pore pressure minus the mud weight. So obviously you want to have such sort of indication, because differential pressure directly impacts the penetration rate. Was these runs were affected by the dynamics? What kind of drilling parameters that had been used to drill these wells? And so those are a lot of questions that come to your mind. So these diagrams or plots cannot be used in isolation. As such, we need to further qualify this with more information. Now, when it comes to drilling parameters, a very good starting point on the right-hand top picture that you see, it is extremely commonly used, a good starting point. It is mechanical specific energy against the penetration rate. So obviously, for those who haven't used this in the past, our intent would be to have a least possible energy spent for a highest possible ROP. So you want to be somewhere closer to this area. And each one of these BHA, notice the one here is a huge spread of energy, but your penetration rate is extremely low, less than 100 feet an hour. So it doesn't tell you much that this is not a good run. Look at the gray lines. It is slightly better, and your energy levels are lower. Energy level needed to drill are lower. At the same time, it has given you a penetration rate of 300 feet an hour, close to 300 feet, or maybe between, say, 150 feet to 300 feet an hour. Look at this run. So now, once you have identified this, you can take it further and break it down. For example, picture on the left top, what is it saying is what kind of hardness that this well has drilled along with the percent of the footage. So this x-axis bucketizes the hardness. Rock, when we say rock hardness, we are talking about the UCS. So obviously somewhere here is about 3000 psi. Notice the hardest is about 3000 or 3500 psi that we have drilled. So this will give you, when you compare two runs, two BHA runs or a section from one well against the other, it is not a bad idea to compare, are we drilling the same formation? Even though you might think on a 70-degree to 90-degree well, you are expected to drill the same formation, but obviously it doesn't happen all the time, because if you are drilling in an environment which is a meandering river, so you are going left and right, and you are changing your drilling environment or environment of deposition of the rocks, and their hardness could change. Now look at the picture here on the left bottom. Here we are trying to evaluate whether each bit BHA run, what was the torque spread? This will be an indicator of if there was any dynamic issues, or was it drilled with a higher torque or lower torque. It would indicate if the bit was very aggressive or not aggressive. So obviously the green trace that you see has the slightest variation in the torque. So I would like to think that this bit run had a very consistent and the stable run. Of course, this has to go hand in hand with your ROP and the footage curve. Now, one on the left, this is also extremely important. This is torque against axial load on the x-axis. What is axial load? Axial load is weight on bit per square inch. Why do we want to see per square inch? Because you could be comparing two wells, drilling in the same rocks, but have a different hole sizes. So in those cases, somehow you need to be able to normalize those readings and see that what kind of force or the weight on bit per unit area has been used. And this slope of this, for everybody's ease of understanding, I would like to highlight the slope of this curve is called aggressiveness of the bit. Now, moving on, if you notice, based on the challenges that we see, and you can divide the trajectory, means given everything being equal, 0 to 30 degree, not much of a challenge. Vertical well, your hole cleaning is not a challenge, simply because that is the difference between, let's say, the annular velocity and the settling velocity. 30 to 60 is slightly more challenging, simply because here the other dynamics and everything starts playing. As we are losing the gravity action force of the gravity, as we are picking up the inclination, so obviously the drilling mechanics and drilling dynamics change, and we start looking at different dysfunctions. So 60 to 90 degree. Now, if you look at the curve on the right, and this is purely arbitrary, but given everything being equal, if you notice, wellbore positioning challenge, the survey challenge, is maximum for the well 60 to 90 degree, because if it is a horizontal, 90 degree horizontal, you turn east-west, your survey errors are possibly the highest. But thankfully, these days, we do have algorithms taking care of this. So also this is probably not much worry, but obviously the challenge is much greater than wells which are 30 degree or 60 degree. Similarly, drilling dynamics challenge becomes very high on 60 to 90 degree wells. Why? Because as you increase the inclination, your ability to add stiffer pipes in the bottom hole assembly is not there much, because this will work adversely for you, because your torque and drag issues will start. As a result, these are most difficult wells. Drilling dynamics issues emerge in horizontal or a high angle wells. Torque and drag obviously is a major issue. Hole cleaning, it is a, I would say, if I have to rank these issues serially, then hole cleaning, torque and drag issues are the biggest issues that you have, or challenge that you have, on a horizontal or a high angle well. Of course, the swab and surge too. Swab and surge is a pretty much one of those issues that you can model and sort it out, and you can kind of change your trip speed. So based on these points, I will move on and start kind of giving you some pointers on all these few topics that we have discussed. For example, drilling dynamics. Now, drilling dynamics is a kind of very important aspect in a high angle wells, because of the fact that dynamics plays a major role in drilling speed. Unfortunately, cutting the rock or destroying the rock, it's a destructive process and you can't avoid it. So only choice that you have is managing those. And look at the bit here, PDC bit here, that has lost its blade because of the bad dynamics, backward wear, or the stabilizer that is completely worn out at the bottom. Or on the right, if you notice, the bottom hole assembly element has developed a crack, and this crack is due to the cyclic stress. So undesired BHA failure can really slow your progress down, and it could kind of force you to trip in and out. And I have a case history towards the end of this section, which is a very good representation of this. And as I said, high angle wells have more prone to dynamics. Now, when it comes to dynamics, what is the reason for dynamics? Reason for dynamics is a natural frequency. A drill string has its own natural frequency. So as soon as your RPM or even the drilling fluid, when you are pumping the drilling fluid, if you match that frequency or the resonating frequency, drill string starts vibrating. That is one reason. Bit and BHA interaction. Different bits and different BHA will interact with the formation very differently. and that may cause drilling dynamics issues. Interbedded formation. In a formation, if you are going from, say, softer formation to harder formation, obviously you come to pretty much like a break in the progress. And that is where that could easily trigger the drilling dynamics. Not to say that drilling practices, if the driller is not really careful and not following these good drilling practices, he could easily trigger some drilling dysfunction due to not following the proper process. And we'll talk about that in a bit. Bit and formation interaction is also very important. Some formation, harder formation specifically, are very prone to drilling dynamics issues. Now, when it comes to natural frequency, the good simulation models are available. These are computer-based simulation models that will often give you a pretty much parameter map whereby you can look at the parameter, and based on your drill string geometry, based on your trajectory angle, you can probably follow the safe drilling window and have, pretty much like a smooth drilling. But that is not always true, though. Now, let us say, what are the different modes of vibration? Of course, we all know axial vibration along the axis of the drill string. These are caused mostly in case of roller cone bits. Lateral vibration, which is across the drill string axis, and of course the torsional vibration. Now, there is a relationship between these vibration modes, which is called coupling. If you have an axial vibration, at the surface, you are anchored. Your drill string can't move. So if that is the case, you see a lateral vibration, although the trigger is due to the axial vibration, but you may also experience lateral vibration. So this phenomena is called the coupling, vibration coupling or coupling. So these three types of vibration mode. Now, beside these three, the drill string, especially the bottom hole assembly, could also kind of have an off-center rotation, which are called whirls. And these whirls could be forward direction or backward direction. Forward synchronous whirl or backward synchronous whirl, as the industry calls it. And this causes, excuse me, and these are really very detrimental, especially to the bits and to the bottom hole assembly elements, because this could cause the kind of blade breakage, cutter fallout, or even the stabilizer wear, and you could be drilling an undergauged hole, if not the failures of electronics. What you see on the right in the bottom of the page is a rotary speed and a weight on bit curve coming out of the simulation, computer simulation, and it shows you, this is a generic though, it shows you the safe, stable drilling window. So this green area is the safe, stable drilling window that you may want to follow. But that is not the end of it, though. Based on your ability to measure for last about, say, 10 years or so, when our capability of vibration measurement has increased significantly, we noted that the drill bit interaction with formations, especially in case of harder formations of, say, around 20,000 psi or harder, we see high frequency torsional oscillation. At one time, this was called as a chatter. When we did not know much about it, we saw it and we realized that, oh, this is one of those things that happens because PDC bit is kind of going backwards and forwards. But later, when our ability to measure increased and improved, and we realized that this HFTO is very detrimental to the bottom hole assembly. And obviously now we have the measurement capability, and we measure it. We know a lot more about it now than we used to know 10 years ago. There are lots of digital solutions available to handle those. But I'm not talking about digital at this point of time. I am sure for each vibration mode, you have seen these traffic light signal type of things stuck on the driller's cabin right in front of him, that if he sees green means no problem with the vibration, he should proceed, and everything is hunky-dory, everything is, the well is drilling very smoothly and no action is needed. Now, yellow severity, this is one of the companies that uses in the past these three lights or 4 lights, and based on each vibration type, there will be different charts. Yellow severity will indicate that yes, this is getting a little worse, so you need to watch out. Exactly same as say traffic light. In some countries they have a yellow light too, and here if you are staying too long in the yellow light zone, action is needed. Although the nothing may have changed, but this yellow may turn red immediately. Similarly, red light, based on the vibration mode, will give you a different solution. If it is a torsional oscillation or torsional dysfunction, it might say that, hey, decrease the weight on weight, decrease the RPM. That is a possibility. Obviously, the driller has to watch the critical rotary speed, because you are always working on a window. Now notice the chart here. This is the simulation window for weight on bit and RPM combination, and what kind of gravity forces, GRMS shocks that BHA is experiencing. Notice the red zones. These are no-go zones. Now, what is so important to understand here, that this is for a specific 128 RPM, 21,000 pound weight on weight. It will change for each combination, but the challenge here is to understand that these red peaks are very sharp peaks. If you want to move from here, you could just change your weight on weight by 2,000-3,000 pounds, or your RPM by 5 RPM, and you would just get off this cliff and move into the green zone. If it is a very narrow window, you might like to get down from one red peak and you might end up getting into another red peak. So this is extremely important to understand, that these natural frequency windows are very fine and small windows, and you could hop in from one window to other based on how you change your parameters. So it is always advisable not to change everything at once. If you are changing weight on weight, let's change the weight on weight and wait for a few minutes to see if you are off that red peak or not. And if you are not, then maybe you want to change your RPM. And hope it is making sense. Also, it is very important to understand that when you run in a high angle wells, or in any well as such, when you run a bit for the first time, or when you wipe a trip and go back in the hole, it is always important to re-establish the pattern, bottom hole pattern of the bit. How do you do that? You just gradually break the bit in, because this could be a trigger. More so if you are drilling with a similar combination, a 5-bladed PDC bit followed by another 5-bladed PDC bit, it is easier that it will engage exactly in the same way. But if you have a roller cone before and you are following it up with a let's say PDC bit, you have a tri-lobed pattern established at the bottom, and now you are following it up with a different pattern. So obviously it is good idea to slowly drill about half a feet and then apply the required parameter. Now, negative drill break practices. What is negative drill break? Drill break when your drilling rate goes faster. Negative drill break, if you encounter the harder formation and you are drilling a softer formation first, and all of a sudden you try to penetrate a harder formation, so you are pretty much hitting a break. In those cases, in the high angle well, there is a high likelihood that your gauge cutters will be damaged. And in those cases, the work rate on the different cutters will change and the bit will be destroyed within no time and you will be pulling out of hole. So in those cases, it is always good idea to break this. If you have a negative drill break, there are negative drill break practices available with every operating company, every directional drilling company and MWD company. You follow that up and go ahead. If you are doing a wiper trip, exactly the same thing, ease down your bit. It is very easy when you are close to the bottom of the hole. If there is any fill, you may not recognize it and you may hit the bottom very hard. So as you come to the close to the bottom, it is always good idea to slowly, gradually ease the bit onto the bottom and then go ahead and drill. So there is a lot of new digital solutions are available to basically give you a more information of what's happening downhole, and that is something that helps a lot these days, and every operating company around the world are using these. Now, in a high angle well, BHA design, what exactly is important to understand here? Let us look at this, a very high angle horizontal well. Now in this well, since it's a long lateral section, close to about, say, 2000 meters, so your torque and drag issues could be severe and you don't have an option to use heavier elements like heavyweight drill pipe here to push it to withstand the dynamics. So obviously in those cases, what is your choice? So what this paper describes is you can iteratively increase the number of heavyweight drill pipe, 1 or 2 heavyweight drill pipe in the bottom hole assembly to withstand the dynamics, so that your torsional oscillation is basically minimized, as well as it withstand the lateral vibration also. Now, I'm sure many of those drilling professionals would know that as you increase the inclination, notice the component of the force that acts on the bottom, component of weight on weight that acts on the bottom is cosine of the inclination. So when it is cosine of the inclination, at some point of time, you lose, it is like a diminishing return. So you cannot use heavyweight drill pipe and anymore at the bottom because it starts working against you. And also wellbore tortuosity, this is very important to understand. If you have a lot of vibration, there is a possibility that your tortuosity of the wellbore is very high. If the tortuosity is high, your torque and drag is high. If your tortuosity high, it could trigger the dynamics movement. So obviously mud lubricity, and there are enough available drilling tools. For example, there are say anti-stall tools available using motors with rotary steerable. That is also very common solution and used nowadays very frequently to decouple the drill string. It's a very kind of common solution these days, drilling horizontal wells. Is it making sense for everybody? Can you all with me? I'm assuming you all are, so I'll just continue to move on. Now, look at this case history, the well that I was showing before. All I would like you to concentrate here, this is a MWD measured downhole RPM in the track almost in the middle. Now, what do you see here? Red line is the maximum RPM over the fraction of a second. This is how MWD measures. Black trace in the middle is the average RPM, and the blue trace is minimum RPM. Now, to look at this and try to understand what exactly is telling us. It is telling us that the blue line is almost coming to zero. So what it means is bit is almost coming standstill. It is ticking and then starts spinning. So this is an extreme example of stick and slip. As you apply more torque from the surface, bit slips and it rotates. So this process, what is it doing to the BHA? It is accelerating, deaccelerating. So obviously it is causing a lot of shock in the tool. And as a result, you have one after another failure. There's a reference to this paper, SP 104388. You can read it if it makes sense for you or if you are interested. And there was about 5 failures. Now, what was the solution and what was done? Notice here, these two traces, average, maximum, minimum, are very close to each other. So what it means is drill string has a very low torsional vibration, almost non-existent. As we are going through interbedded formation, you see a little bit here, and it is drilling smoothly. Now, in this case, these are the sticks and slip status 0 to 7. 7 is extreme. Notice here, it is almost 6 all the way down. 7 indicates backward world for the specific company. So what did we do here? We had to act because we can't drill the well with so many failures. It is tripping in and out. This is an offshore well. So obviously we made a change in the BHA. And what was the change? We took a bit and we engineered it with some potential solution, depth of cut control, to mitigate the torsional oscillation. We added some heavy weights in the drill string somewhere here in the BHA. Also, since it was back-to-back failure, we added a torsional failure. So we added a roller reamer and we went in and we finished the entire horizontal section. This was a multilateral well. The one that you see here, we drilled the motherboard, we came back out, we drilled the multilateral 1, we pulled a little bit back, we drilled the multilateral 2, and after several days, we came out a very successful well drilled with a single bit and single BHA run. And later, since it was something that we needed to do it on an urgent basis, later we dropped the roller reamer because we were always concerned with the possibility of dropping the roller that may aggravate the situation also. So we dropped it and this project continued smoothly after that. Now, we'll talk about torque and drag a little bit. Now, why torque and drag is important? At the planning phase of the well, one needs to know the friction factor. What is the friction between drill string and the well bore, open hole, so that you can decide how far you can drill or what could be the drill pipe that you could be using, so that what would be the operating torque needed. Where is the position of the neutral point? Because you want to place a drilling tool, for example, a drilling jar, not close to the drilling point, of course, the neutral point. Drilling jars will work either in compression or in tension, but obviously it can't be close to neutral point. So your understanding of the neutral point is absolutely necessary. So with that in mind, when you run the simulation models, you would simulate different friction factors and what comes to close to your actual condition based on what you have seen on the rig, or you may, and you can use a different models. There are different models available, and you could also kind of simulate what is the surface torque that is expected. So you go bottom down approach and you come up with a friction factor, neutral point, as well as the surface torque in all conditions, like during running in, what would be the hook load, during tripping in, what would be the drag. So all those informations would be available. Also, the torque and drag would give you the cyclic stress, because remember, the drill string, it in a high angle well is not straight. It is somewhere, it is sagging, and when you are rotating that BHA with a high RPM, say about 100, 150, what exactly is going on? It is going through cyclic stress of compression and tension, compression and tension. One side of the drill string is under tension while the other side is under compression. And when you do that, you are really stressing your pipe big time. And that has to be calculated, seen all the time during the planning stage. Now, in a horizontal well, because the challenge is that we are unable to supply much weight on weight down. So obviously, one of the things is in a smaller hole size, it is possible to use part of the drill pipe. Drill pipe is obviously, you are assuming it's in tension. So there is a big no-no to run the drill pipe in compression, but there is a lot of work and theories available. A lot of work has been done, and it is suggested by many people around the industry that you can run the drill pipe in compression. Obviously, you cannot run it all the way to compression because of the helical buckling and all. So it's about 80% with some safety margin, let's say 70%, and you can run the drill pipe in compression. Right. Now, when you are running the drill pipe in compression, obviously something that you want to know, what is the critical buckling load? So I want you to focus on this formula. Notice that critical buckling load is proportional to inclination, sine of the inclination. So what does this mean? As the inclination increases, your buckling load increases. So obviously, very good thing. So in a horizontal well, this is where the theory coming from, that at a high angle well, you can use part of the drill string, part of the drill pipe for weight on weight application. Notice another, the radial clearance between hole as well as the outer diameter of the pipe. This R stands for radial clearance. So it is only for the smaller hole sizes. When I say smaller, means 12¼ and below. Notice as the radial clearance decreases, buckling load increases. So you are able to apply more weight on weight without being buckled than if you are a radial clearance, which is less. Very important formula, but mind you, this is not the sole formula used in the industry. This is Dawson-Parsley. There are other Chen and Cheatham. There are about 15 of those that is commonly used. Now, for those who are not used to seeing torque and drag diagrams, you would notice in any torque and drag diagram, it will give you the helical and critical buckling forces, weight on weight needed. And if your drilling line, so this is pickup, so drilling line is red. I'm not sure you can see it with all these busy lines. See this red line? As long as this red line doesn't intersect, you are good. And obviously it will give you sinusoidal buckling load 45, say this in this specific case is 45.4 kilopounds. And so you are looking at this space here. So this is what is very useful, and it gives you the idea of sinusoidal buckling helical buckling. You do not want to helically buckle your drill string. You could, if needed, you could remain in sinusoidal buckling stage for a little while before you have to come out of it. Of course, it gives you an idea of where the neutral point is. Notice this is zero line. So if you take this up, somewhere here it is changing from compression to tension. This portion is tension. This portion is drill string is in compression. And of course, the fatigue safety factor, that is also very important, that how far you want to fatigue your drill string. Similarly, the models will also give you a report where it will calculate the friction factor. What exactly is the calculated friction factor? What kind of, notice a very interesting thing here is it gives you that here in the rotational discontinuity section, it says 11 revolution and 190 degree in this horizontal well. What does it mean? It means when you are on the surface, you start rotating. Because of the torsional elasticity of the drill string, till you rotate the entire string 11 times, it is just an estimate, 11 times and 196 degree, this is when you are able to transmit your rotation to the bottom. Similarly, all the stress, this minimum yield safety factor is here. See, the buckling loads are here. So this is the standard, just wanted to kind of summarize it for you. Now, this is a very important slide. If you have an aggressive bit or some drilling system, they may cause hourglassing. It is exactly shaped like hourglass. Or it may cause corkscrew or well bore rippling. Now imagine if this is what you have in the well bore and you are trying to run your liner, your friction is too high, or you are running your drill string through these. There would be a major issue in transmitting the weight. So obviously, this is related to this paper, describes all this and says it is a paper that describes various different rotary steerable system, and what have they found out is one of the rotary steerable system, continuous proportional steering, has lot less average tortuosity. This is right here, compared to point the bit and push the bit system. Those are very commonly used 3 types of rotary steerable system in the market. Is it making sense, guys? Okay. I did mention that there are a lot of different buckling models or drill string torque and drag models are available. I have a small list, and this is like kind of tells you various different models that is available and what formulas that they use. All these details that I teach normally with a work example in some of the courses. Now coming to drill bit now. Drill bit also causes, drill bit is the first BHA element that touches the formation. So obviously this is first affected by the formation. And based on the drill bit, if the drill bit is very aggressive, generating a lot of torque, the same torque is transmitted all the way to surface. So now let's have a look how drill bit, like I said in a slide before, if you have a roller cone bit, your torque fluctuation is very less. This is weight on bit and torque, rotary torque, reactive torque diagram. So obviously slope of this line is called aggressiveness of the bit. PDC bit has a lot bigger fluctuation. As a result, it is lot more aggressive. And every other bit lies, based on the design you choose, somewhere in between. So there'll be PDC bit A, PDC bit B, and as a drilling engineer or as a directional driller, you will be required to choose a bit that best suits your application. So notice what I'm saying here is aggressiveness of the bit, which is termed as mu. Very aggressive bit is known to trigger the drilling dynamics issues. Now, drilling dynamics issue could also be triggered by the formation, very hard formation, like I said, different things during the management of the drilling dynamics. Now, a engineered depth of control helps, and I'll talk about what it is. Now, hybrid bed technology, which has been introduced for about last 6-7 years, which is the combination of the PDC as well as the roller cone element in the same bit. This is a very kind of interesting for the situation because its aggressiveness is in between. It is giving you some sort of aggressiveness, which is a PDC, and also being a roller cone element at the bottom touching, it also kind of minimizes the torsional vibration that you expect from a PDC bit. Now, let's move on and see. Remember I said that as the bit goes, as the formation changes from hard to soft, soft to hard, this triggers vibration. So obviously, why? Because you are all of a sudden you are stopping, or all of a sudden you are going. So this is one of the reasons it is really important to have a good map of the drilling environment, which includes the hardness of the formation. Now, what is engineered depth of cut? Each cutter in the bit moves in a helical direction because every rotation it is going down, it is taking a helical path. And if you take that path, probably in one rotation, each cutter has moved based on its position from the center outwards. It has traveled a distance, vertical distance, little bit more or less if it is towards the center. What are we trying to do in the PDC bit is, if it goes very far, and this distance is called depth of cut, if it is going too far, we are engineering it so that the blade comes in contact with the formation and it slows down, it takes away the torque spike. Does this make sense, guys? Now, you would ask me a question right here that, hey, yes, if this is the case, this is done for a particular ROP. There are new bit designs or new bit models that pretty much uses automated kind of depth of cut control, adaptive depth of control, they call it. They put the piston in, and each of these piston on the top end of it is a diamond crusted ovoid. So this ovoid kind of comes out and goes back in, comes out, goes back in. So it kind of facilitates this process instead of blade coming into contact. So this is going out in all the time, immediately, based on how fast you are drilling. Now, one of the probably most important topics, probably I would think for today, is the hole cleaning. Based on the hole size that you drill, you have a lots of cutting that coming out of the hole. So if you take the standard density of the cutting, and you notice if it is an 8.5 inch hole, you are drilling at 60 meters an hour, or little over 60 meters an hour, you are generating 2 cubic meter of cutting every hour. So now, if you are generating 2 cubic meters of cutting every hour, that has to come out of hole, simply because there is no way you can drill faster unless your bit face is clean. Of course, these cuttings, if they do not escape the hole, they will settle down on top of the stabilizer. They will make the cuttings bed maybe, and they may cause stuck pipe. They may, of course, say fracture the formation even. I'm sure many of you have seen it in your career. And it is highly relevant when the drilling motors are used, because remember, in motor, you are not spinning all the time. You are steering and rotating. So during rotation, cuttings are coming out. While steering, you are not spinning anymore. So you are not agitating the cuttings. So these cuttings are not coming out. So it is extremely important to understand that hole cleaning is very important. Otherwise, it will compromise the rate of penetration. It can have a BHA loss, stuck pipe, and many other issues. Now, what are the factors that dictate the hole cleaning? Of course, inclination for sure. Remember on the slide earlier, we have said higher the inclination is, cuttings tend to settle low side of the wellbore. This is what's happening here. Cuttings are settling in the low side of the wellbore. Annular velocity and flow regime. And what is the velocity in the annulus? In the vertical hole situation, it is really easy that your slip velocity, how fast the cuttings are going down, and if your annular velocity is much higher than the slip velocity, so it is like cuttings falling, however annular velocity is pushing it up, it will come out. But as the inclination increases, obviously you are losing the annular velocity's effect is diminishing, and other factors start playing in, like drill string rotation, annular eccentricity. Is your annulus, is your drill pipe sitting right in the middle? Because remember, if the drill pipe in a higher wellbore, most likelihood is it is sitting at the bottom, so it is creating these channels. If that's the case, along these channels, the cuttings are settling. Penetration rate, how fast you are drilling, is creating annular load. And that is extremely important to understand, that if you cannot clean the well, only one solution to continue to drill is to reduce your penetration rate, which is not what you want to do. Of course, there are other factors like drilling fluid properties, PB, YP, cuttings character. Now notice, with all these different factors, computer models are available, but these are complicated computer models. But let's talk about some factors now. A drag force within the laminar flow regime, cuttings move up the annulus, they are just dragged. However, in case of turbulent flow, the cuttings, they pretty much hop. They hop through the annulus and they come out. Now, the question that you would probably, or you may have in your mind is, why can't we follow just the, say, turbulent flow in the annulus? If you have the turbulent flow in the annulus, possibility is whether your formation is going to get eroded, and your well would be, instead of 8.5 inch, it could be much bigger hole size. So your cementing issues, cementing cost, and various other things, cement integrity. So flow now notice these observations. At 30 degree, annular velocity required to clean the hole is 20% higher than 0 degree inclination. As you go from 30 to 50 to 60 degrees, it is twice as much as needed. So this is why I was using that first slide, 0 to 30 degree, 30 to 60 degree, and 60 to 90 degree buckets that I have created was based on these information. Now, this is important to note that cuttings, they are built as you are drilling ahead, these cuttings bed are being formed. When do they form? They start around 35-degree inclination. And between 45 and 65, these cuttings bed start slipping down, avalanching. If that is what is happening in your well, possibility is it will be sitting around your stabilizer. It will be causing a torque and drag issue. You may not be able to drill very far, if not worse, which could be packing off around the stabilizer and losing circulation. Now, in a low angle wells, you can get away with the, say, laminar flow. However, in the turbulent flow is needed in a high angle wells. But mind you, turbulent flow, when the drilling fluid escapes the bit through the nozzle, there's a big turbulence in the front of the bit. And gradually, as it moves up the annulus, from the turbulent flow, it comes all the way to laminar flow and it escapes the annulus at the surface. Now, a very important point here that I want to mention is RPM. We talked about RPM and how important the RPM is. RPM helps you, yes, but it is not that you can cranking RPM up will help you all the time. It is seen that about 150 RPM or so, based on your inclination, effect of RPM levels off. So if you have a annular ECD measurement device in the bottom hole, you will see that RPM, effect of RPM diminishes at about 150 RPM. And this is where you have to stop and say, do I really want to spend more energy? Because more RPM means you could be causing the casing wear. That is possible. Because these horizontal wells take a long time to drill. Your bottom hole assembly could be in the hole for a longer period of time. So obviously you could be running a casing wear model too, giving it a thought that how far I can run it, how far I can drill without causing much kind of damage to my pre-existing casing. Now, look at this hole cleaning case history that I have. This is an ECD tool in the hole. With MWD, there's a possibility that you may have an ECD in the hole. And notice the trend changes. This is the normal penetration rate. As we are penetrating, cuttings are coming in the annulus, and you gradually see the ECD increasing. All of a sudden, penetration rate increases because of softer formation, and cuttings start loading the annulus and ECD turns higher. Now, if that is the case, what is the solution? You slow down your penetration rate unless you want to increase your flow rate and RPM and the other things to see whether this is helping you to bring this curve in line. So in this case, however, they slowed down the ROP to 150 feet an hour. Flow remained the same, 750 GPM. And guess what? We came to very normal trend that we have seen in the past, because now the penetration rate was lower. So notice the slope of the line is much lower. Here we conducted a wiper trip. So as soon as we conducted a wiper trip, the cuttings load in the annulus was out of the hole. So obviously this line has come much kind of straighter compared to what we had here. I hope it all making sense for you all. Now, I would like to leave the last few minutes for some question, and before that, I will summarize. Now, hopefully, you will get the idea that when you are analyzing the performance, you need to qualify these performance with different factors that could affect these performance summaries that you are generating. Given the all aspects are similar, a high angle wells have a greater challenge, and those challenges could be dynamics, hole cleaning, swab inserts, wellbore positioning. So during the planning stage, you need to address all those. And at least I have seen a lot of operating companies creating a risk register that these are the risks. This is the likelihood of happening. So if I prevent it, how would I prevent it? Torsional fluctuations are common with PDC bit. Axial is common with roller cone bit. And you cannot allow a aggressive bit has a higher torsional oscillation, and they are more prone to stick and slip, and you want to possibly avoid it. Now, drilling dynamics reduces the efficiency, and drill pipe could be run in compression in high angle wells. This is a pretty standard practice. If you are working as a directional driller or if you are working as a drilling engineer, you may have seen this. Drilling different RSS tool impact the wellbore tortuosity. We have seen that as PE paper. Cuttings in the annulus move by the drag and the lift force. Now, in the laminar flow, drag forces are dominant. In the turbulent flow, lift forces are dominant. Effect of RPM levels off at around 150. So there is no reason for you to spin faster than 150 for hole cleaning. If you want to drill faster, obviously there are other theories that exist, other practices that exist. And ECD tools are available to drill. With that, I'll open the floor with questions. So I'm sure Iftikhar may have had some question captured. How do I see those?
Yes, sir. There are a lot of questions that asked.
Okay.
You can just scroll down and you will see.
Okay, let me start from the top.
Yes, sir.
How am I doing with time?
Yes, sir. You can go ahead.
Okay. Okay, what are your suggestions for horizontal drilling in the coal seam? Okay, I think, Arun, you and I have met in the past life, if I'm not sure. So anyway, CBM, coal bed methanes are regularly drilled in India, Australia, and several places in the world. This is one of those wells where it is like coal has a very different property, petrophysical or mechanical property compared to the other rock types. And in the coal bed CBM work, based on the coal types, certain coal types are very frequent to cave in. So in those cases, the operators, although the technology is available and it's being drilled, but normally if you bury the BHA, they come out, leave the BHA and go, and they are drilling with the cheapest BHA possible. But here, since you are asking for the solution, I think mud solution is the better. Also in the coal bed, when you plan your trajectory, you do not want to be very aggressive and optimistic doing any directional work in coal. You just land above the coal and drill straight down the coal. One thing that you want to see is the type of the coal, whether it allows drilling across or not, and follow the like a direction of stress. So this is one of the things very important. Now, Muhammad Zubair asked me the question, what will be the position of roamer radar directional BHA with full gauge or under gauge? Okay. Roller reamers I personally prefer 1/16th under gauge. There are customers, I have worked for Chevron, British Petroleum, and several other companies. They all go at least little bit under gauge. One of the reasons that they want to go under gauge is they do not want engagement of the roller reamer with the well too much, because there is still remains a concern that you could leave with too much engagement with the reamer and the well bore, you might leave the rollers in the hole. So it is always recommended that you have a roller reamer which is at least 1/16 under gauge. Here's a question from Ahmed Saraf. Can you discuss the influence of wellbore tortuosity on drilling dynamics? Very good question. Does the question still valid, sir? Because I think in one of the slides, I have mentioned that tortuosity of the wellbore could be due to hourglassing, corkscrewing, two-dimensional or three-dimensional. And it is several rotary steerable systems are known to generate, point the bit system specifically, known to generate, if you are drilling too much in a one direction, with one orientation, it could generate a tortuosity. So also very important to understand that this is unfortunate that experience of the directional driller also starts playing here, which cannot be quantified, because experienced directional driller also uses the natural tendency of the drilling tool and let it float in the drilling window instead of kind of causing too much of downlink, too much of what you call orientation with the rotary steerable. And because if you are drilling a too much of oriented, or when I say oriented for rotary steerable, I specifically mean that if you are downlinking it, instead of creating a straight wellbore, you are creating a tortuous wellbore. Tortuous wellbore means subsequent element, when it comes to this tortuosity, they generate this vibration. So obviously, this is something that we need to keep a watch, that how many downlinks and how the well was drilled with what kind of steering forces, if that's the direction. I hope I'm answering the question. Selection of the bit and the hardness. And what other factor? Okay, I did not get the question. I could not understand the question. Bit, obviously, if it is a PDC bit, based on the hardness, you would select the cutter type. And in a bit world, cost of the bit goes astronomically high based on the cutter. There are some cutters which are impact resistance. There are cutters which are wear resistance. So if you are drilling through very abrasive formation, what kind of wear that you expect? You would possibly expect a wear. So your cutter type selection should be wear resistance. It is not that easy. There are times that drill bit engineers often use mixed cutter. So in some specific areas, like a gauge, they will use impact resistance cutters. And in the face of the bit, they might use wear resistance, because position of the cutter in the PDC bit dictates the work rate, because the cutters that are towards the gauge, they are doing the biggest circle. So their work rate is much higher than those which are in the center. So obviously, you need to be extremely cautious about what you are trying to use for drilling. Where is the cutter placed? And based on placement of the cutter, you want to go wear resistance or impact resistance. Current BHA recommendation for long horizontal wells, heavyweight drill pipe in the vertical section. Okay, very good question. I may have addressed it in the past. As a my personal experience suggests, and I have it in several SPE papers too that I have authored, I personally do not want heavyweight below 45 degrees, anything higher than 45-degree inclination. Because if you look at the cosine curve, you note that cosine varies, and after 45-degree, the cost benefit, it doesn't help anymore, because you are working against yourself, increasing the torque and drag. So this is my personal experience. I do not put the heavyweights below 45-degree. And sometimes there is a term in the industry that they call it push pipe. They use the above 45 degree, because in a horizontal well, you are unable to go further. So obviously you are trying to pull the pipe. So you are calling it pushing the BHA. So they call it push pipe. BHA for 1,000-meter horizontal section. Muhammad Zubair asked the question, BHA for 1,000-meter horizontal section. Zubair, we have drilled much longer horizontals, 3,000, 4,000-meter horizontals. And the BHA would be very, when I say standard means, of course, you cannot change from bit all the way down to measurement. You cannot change it. Since it's a horizontal BHA, I would definitely like to place a MWD tool capable of transmitting vibration mechanics, and also, if possible, a pressure data. So this is a must. Behind this BHA, when I say BHA, I purely means MWD, LWD. I would certainly use jar. A lot of people do not use jar. For the jar to be able to trigger and have the impact, I would rather have a couple of heavyweights on top, because you need to have an impact. I will have a couple of heavyweights, and there are jar calculation models available with the jar companies. They will give you a specific recommendation, and you run these recommendations through torque and drag. Can we do jarring in a coal seam? I think this is not really recommended, and reason being, coal tend to cave in. More impact that you have, coal starts caving in. So obviously your practices are to avoid jarring, to ease the BHA out in the event of a stuck pipe. This is probably the most difficult situation, I understand, but most of the customers, I have worked in Australia on CBM projects for a few companies, and they tend to avoid, they don't even use jar in the coal, and they straight away leave the BHA come out. They will have the cheapest BHA, and if they can't release it in very fast, they will come out of hole. Not the very good answer, I know, but hey, that's a cost. Lowering of the casing in completely different from the vertical wells. Yes, you are right. What are the basic things to keep in mind? Design the casing for the horizontal wells. Okay. What I have seen in the past in the horizontal wells are, they will use mixed casing elements. When I say mixed, means different grades of casing from high and low, because that they want to minimize the torque and drag effect, as well as the, you are going down, you want to ease it in. So that is a possibility. Different casing running programs gives you a different kind of burst and collapse pressure. I think one of the very popular program is to gives you a, you are dictated by the burst and collapse, but only way to kind of deal with it is you compare your burst and collapse against the casing that you are running. And if you have a torque and drag issue, then use slightly better or heavier casing at the horizontal section and go lighter on the top. I personally, okay, Muhammad Zubair asked me a question again. Can we use roller reamer in the drilling horizontal in the coal seam? I would think that I would, unless you have an experience, some sort of experience, I will avoid using anything that interacts, because you already have a stabilizer or two. Adding extra, unless you have a torque issue that you are handling, can we handle that with the drilling fluid? That may be another thing, because you could be dealing with just a gel mud here because of losses. And in the case of losses, there is a possibility that coal might cave in. So putting an additional fat piece of roller reamer in the hole might increase your chances of getting stuck. Okay, Deepti Sharma is asking me, can you explain the negative drill break practices? All right, very good question, Deepti. Negative drill break, first of all, try to understand what is negative drill break. When you are coming in drilling at 100, let's say 200 feet an hour, 300 feet an hour, all of a sudden you hit a very hard formation. If you don't know that, if you did not predict it, first thing that you want to do is give the drill bit least energy that is possible. I'm sure everybody rode cycle or motorbike. Remember the speed breakers. When you see a speed breaker, you slow down. In this case, you haven't seen the speed breaker because it is 3,000, 4,000 meters down below. So first thing that you do is de-energize the drill string. Slow down your RPM. When you slow down your RPM, you are already helping your gauge cutters. Remember those gauge cutters, they are spinning with a very high work rate. And that is one thing, the first thing that you want to do, and then see if you have a very high weight on weight that you are drilling with, ease your high weight on weight till you have buried the bit in about 1 feet. Once you are in the bit is in the formation about a feet or so, you can go ahead and apply the required parameter and drill as fast as possible because you do not want to trip out. So hopefully I have answered most of the questions. How to torque and drag? What is the problem? We can say, did it okay. What is the how tortuosity associated with torque and drag? Okay, did I answer that? How tortuosity is associated with the torque and drag and what is the problem we can face? Obviously, with torque and drag, you are creating a problem even if you successfully drill it, your casing may not be able to go in. So that is why when we do the planning, you are doing a sensitivity analysis and applying certain tortuosity to see how far you can go. If your tortuosity is very high, mind you, you cannot drill very far because at some point of time, your torque and drag is very high and your lockup might happen and you cannot push your drill string, which is sitting on the low side of the wellbore, any further because of the very high tortuosity. Does it make sense? Okay, here is another question. Julia Amber is asking me, can you explain critical buckling force to hole inclination graph? Okay, let me go back. Let me go back to this specific. Okay, I think here. Okay, Julia, this what is a critical buckling load? Critical buckling load is, first of all, understand this, what exactly it means. It means when does the buckling starts? Means your drill string is sitting right in the middle of the wellbore and you are applying the weight from the top. Your drill pipe is under tension, bottom hole is under compression, and all of a sudden what happens is, since you are unable to push through, your drill string starts deflecting. There's a lot of terms that they use with it. So just look at like a snake that is going back and forth. So this is what critical buckling load is. Now it is, critical buckling load is Young's modulus times axial moment of inertia times weight on bit that you are applying and the sine of the inclination divided by the radial clearance, the clearance between the wellbore and the pipe. Now, obviously, what it means is, as you continue to push this pipe through, all of a sudden you would note from sinusoidal buckling, which is the buckling in one dimension, all of a sudden it will go to helical buckling. So this is why it is extremely critical to understand that yes, you can buckle your pipe sinusoidally to an extent, but it will spring into helical buckling immediately. So you need to be extremely cautious that if your critical buckling load, let's assume, take a number, 45,000 pounds. You do not want to go any closer. You need to leave a safety factor, which could be 10,000 pounds. Obviously, once you do that calculation, you will see that. Hopefully, I have answered most questions, I suppose. With that, I personally like to thank all of you for attending this and showing interest. Is that anything, Iftikhar, you want to say?
Thank you, sir. Thank you, sir. And thank you all the participants. I know you guys have a lot of questions. So what we'll do, I'll just share a quick feedback form
Yes.
on the community post on WhatsApp. You guys please go through it. And if you have any questions or any doubts, queries regarding the topic or whatever the sir has told, you can just put it, fill the form, and we'll come back with some answers. So thank you, sir.
Absolutely.
And thank you all the participants for joining this session. And see you soon.
Thank you very much, and you all have a great day ahead of you.
Yeah. Thank you, sir.
Thank you.
Thank you and good night.